Alright, we're looking at limits. And pretty much what we're doing right now, we're looking at limits graphically and numerically. Okay, so two different ways we're going to look at limits right now. We're not doing all the fancy stuff yet. We're about to tomorrow. Okay, but today we're just looking at this graphically and numerically. So, if we wanted to find the limit of this, here's the question we're asking ourselves. How do the values of the function f of x behave? When I say values, I mean y values. How do they behave when x approaches a number? And I'm just putting c there for like some random number. Whether or not f of c is defined. Because sometimes it's defined, sometimes it's not. See, look at this one. F of 0 is undefined. But there is a limit here. Okay, so check it out. This is how you would write it. You would say, find the limit as x approaches 0 of, we'll say sine x divided by x. And below we have the graph of sine x divided by x. And so we can see what it's approaching. Now if it says just like this, x approaching 0, then we're going to 0 from the left and from the right. And so we go up to our function, we approach from the left and from the left and from the right to see where it's going to end up. So where are the y values going to end up right here? What y value is that? 1. So even though if I plug in 0 into x, I would get undefined, they do approach 1. They approach 1 from the left and from the right. So this limit does exist. This would be your answer. Alright, so let's look at some other examples really fast. I give you the answers for these ones. We're just going to analyze them, okay? So the limit of 5 as x approaches 7 is 5. But why? Well, 5 is kind of like, that is the function. That's y equals 5. Or I suppose we could say f of x equals 5. Doesn't matter. It's the same function, just a different way to call it. So if I look at this function, it's going to be at 5. So that's at 5. At y equals 5. If I were to approach 7, let's say 7 is right here. If I'm approaching 7 from the left and from the right up here, what y value is it approaching? It's approaching 5. That's why it's 5. So whenever you have a constant, pretty much that's what your answer is going to be for limits. Over here, we don't have a constant. We have a linear equation or a linear function. And so we go like this. We graph the guy. We got 1, and then we go up 3 right 1, down 3 left 1. Oops, yeah, that's down 3 left 1. And then I have my line like this. Okay. Now, this says as we approach 4, what's our answer? Now, we put 13 right here. How can we get 13 just by looking at this? Yeah, we plug in 4. If we plug in 4 to that, look what we get. 3 times 4 plus 1 equals 13. Oh, that's kind of cool. If we looked at it graphically, we would have to go over to the 4, which we're going to say is right here. And we would be approaching that from the left and from the right. And our line doesn't go all the way there because we don't have enough space, but we would be going this way, and then the other part of the line might be like way up here, and then we would have to go this way, and we know that it's approaching the y value 13. Because when we eventually get to 4, we know that it's going to be 13 right around here somewhere. Okay, so that's how you read those. All right, now let's get to the cheating part, because we all like to cheat, right? No, we don't cheat. But if you have a graphing calculator, this makes your life a lot easier because you don't have to keep calculating things over and over and over. So this says investigate this limit. We know it equals 5, but actually I don't know if it does equal 5. I don't think it does. Here, let's check it out. Graphically and numerically. Alright, so let's look at graphically and then I'll show you numerically. But we're going to use a graphing calculator for this. So if you have a graphing calculator, take it out. We're going to practice. Did you guys write it down? That function? Do you guys know what it was? No?
Minus 9.
Oh wait, hold on. Okay, so it's a big fraction, right? So we have to go parenthesis, and you said x minus 9?
Yeah.
X minus 9. And then close parenthesis divided by what's on the denominator?
The square root of x.
Okay, so open parenthesis, square root of x, square root of x.
And then minus 3, but that's not under the...
Okay, it's not under the thing, so I got to press the arrow to get out of it. And then I say minus 3, and then close my parenthesis. It's very important that you guys remember your parentheses, because your calculator will read whatever you put in there exactly the way it is. It's really literal. So if we don't have our parentheses right here, this x would not... this minus 3 would not be in the big fraction. So we have to have it wouldn't be in the denominator. So here, check this out. Let's graph it. Okay, do you guys remember what the limit said? As the limit approaches what? 9. Okay, cool. You guys got it. As the limit approaches 9. So here's 9 right here. See, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 right there. Do you guys see what the y value is right there, or what it looks like? What does it look like? Is it 1, 2, 3, 4, 5, 6? Okay, so it's not 5. Actually, the limit is 6. And we can see that graphically. Now, your graphing calculator will not show you holes in the graph. Even if you zoom in, it's not going to show you the hole. If you guys use Desmos and you drag a point along the graph in Desmos, it'll show you the hole where it's undefined, which I think is kind of neat. But I want to practice using the graphing calculator. So, graphically, we see that it's 6. Analytically, how do we do that? Well, instead of plugging in a bunch of numbers, like we did before, we can use the table here. So I'm going to actually, I forgot to change the table set. I want to change this to 1 to show you guys what the table looks like. So you hit second, which is right there, and then graph, because that's where the table is. So if I hit that, oh dang it, I have a weird starting point. Start at 8. No, let's start at 8. Let's start at 7. Okay. So second table. So the table starts at 7, and you can use your arrows right here to go up and down the table. But as we approach, look what happens when we plug in 9. What do we get? Error. So we know there's a hole right there. Can you guys see a trend? Here, I'm going to go up one more. Can you see a trend like where these y values are approaching? What do you guys think 9 is? It's 6. It looks like it's 6, right? Just like the graph did. Now, if you want to be more precise, you're not going to count by ones. You're going to count by a smaller number, like 0.5 or 0.1. Okay, so let's try that. How would you do that? So I go back to table set, which is right there. You have to do second and then window. And I'm going to count by 0.1s. So I'm going to go down and write 0.1 right there. So I'm going to count by a tenth. And then let's start at 8.7, right? See, 8.7. Dang it. Okay, 0.1, I have to go up, then 8.7. So I go back to my table. Boom. So it starts at 8.7. I like picking the starting point so I don't have to keep like using the arrows to get where I want. And I'm approaching 9. Look at that. Look, see how they're kind of the same? All right, and then it jumps over to 6.01. So you can notice the trend. You guys see the trend? That's what we're doing. That's how we analyze this numerically, by looking at the successive values that lead to whatever number we're trying to approach. Okay? I think you guys are getting this. You guys are just looking at me like, when are you done? All right, so we did that one. We can do the same thing with this one. Let's go ahead and just plug it in. Can you guys write that down really quick? I don't want to forget. It's e to the h minus 1 divided by h. Okay, so e to the h, let's go back to our graphing calculator. E to the h minus 1. So we have, let's see, where are you? Okay, go right here to our y equals, and we're going to go parenthesis, because we're on the numerator. You have to go e, so we're going to go second, and then natural log, because that's where the e is at, where you're natural log, right there. E to the h. Now the h is like an x. That's our independent variable. And then we had to press the arrow to get out of the exponent. It was minus 1, right? And then the close parenthesis, divided by, and I think there's just an x on the bottom. Did it say graphically or numerically? Numerical? Okay, cool. As x approaches what? 0. It's approaching 0? Okay, so I want to start at like 0.5. No, I want to count by, dang it. I want to count by 0.1s, and I want to start at dang it. He's messing up. Okay, start at 0.1, see, clear, 0.1, I'm going to go up, and that's going to stay 0.5. So let's look at my table. So as we're approaching 0, oh dang it. We should start at negative 0.5. Mr. Patey, stop it. Okay, now look at my table. There it is. Okay, so we're starting at negative 0.5, and we are approaching 0, and look, there's our error. What do you guys think the limit is? 0.7, 0.8, 0.8, 0.9, 0.9, and then 1.0, 1.1. So what's that That's a 1. That's your answer. So if I go back and look at this equals 1. Hey, we did it. Yay. Okay. So this one's actually interesting. I'm just going to show you what it looks like really fast. It doesn't tell you what to use, so you can use graphically or numerically. But if you plug values into this, you're going to get this and this. This will be at -1, and this is +1. That's kind of interesting. It's really interesting if you make your own table to get these lines. And, I mean, this looks complicated, but it's really not. If you plug in numbers, actually, and think about it, it's actually quite simple. Now, does this have a limit? It doesn't. If I say as the limit, as the x approaches 0 of x over the absolute value of x, this does not exist because the left-hand side and the right-hand side approach different numbers. One of them approaches 1, one of them approaches -1. So we would have to say the limit as x approaches 0 from the left-hand side of f or x over absolute value of x. That equals, what does it equal? What does it equal? -1. If I go from the other side, the limit as x approaches 0 from the positive side of this guy, that's going to be +1. So here we have an example where the limit doesn't exist as you approach 0, but it does exist if you approach it from one direction or from the other direction. They're just different.